In this problem, we are given a figure shown, and we are tasked to calculate the slope at A, at B, and the deflection at C. And the best way to solve this problem is by using the conjugate beam method, knowing that our beam here is non-homogeneous. So first, let's solve for the reaction at the support. So by taking summation moment at point B equal to 0, considering counterclockwise to a positive, we have reaction A that is negative, because that will induce a clockwise moment times the moment arm distance of 4 meters plus the 9 kN force times the moment arm distance of 2 meters equal to 0. We can solve for IA, that is just equal to 4.5 kilonewtons. And to solve for RB, by taking summation force vertical, we can see that RB is just equal to 4.5 kilonewtons. And after that, we construct our moment diagram by parts with our reference line along the 9 kilonewton force. So, due to the point load at the roller support, this will induce a moment at point C. So, going from a point load, it will induce a first degree line in the moment diagram that has a value here equal to 4.5 times the moment arm distance of 2 meters. This is equal to 9 kilonewton meter divided by EI. And for the 4.5 kilonewton force on the right, this will induce a moment at C that is equal to 4.5 kilonewton times 2 meters divided by 2 EI. This is equal to 4.5 kilonewton meter over EI. Now to compute for the slope at A, this is the moment of the beam at this point here. So, going from a roller support, our conjugate beam has a support here that is still a simply support. So this is the same roller support as our original beam, and this one here is still a hinge support, because the conjugate beam for a pin support that is found on the outer edge is the same pin support in the conjugate beam. And then next, we solve for the reaction at the support of our conjugate beam. So we let this be R sub A, and this one is R sub B. Then taking summation moment at point B to solve for the reaction at A, considering counterclockwise to be positive, we have RA times the moment arm of 4 meters, and this is negative since this will induce a clockwise moment, minus the area of this triangle to get the resultant on the left side, that is 1/2 times a base of 2 times the height of 9, multiplied by the moment arm distance. This is equal to 2 plus 1/3 of 2 meters, and minus the resultant of the triangular load on the right. This is 1/2 times 2 times the height of 4.5, multiplied by the moment arm distance of 2/3 of 2 meters, all equal to 0. So solving, we have negative RA times 4 minus 1/2 times 2 times 9 times 2 plus 1/2. This is 1/3 of 2, since the center of the triangle is found 1/3 from the base. So we have 1/3 times 2 minus 1/2 of 2 times 4.5 times 2/3 of 2. Shift solving, we get the value for RA that is negative 7.5. Now to solve for the reaction at B, we take summation force vertical equal to 0. So we have RA that is supposed to go downwards since the value here is negative. So this is negative 7.5 plus RB, and then plus the upward load of these two triangles, that's 1/2 times the base of 2 meters times the height of 9 meters, plus another triangle that has an area of 1/2 times the base of 2 meters times the height of 4.5, all equal to 0. Solving, we get RB, that is equal to we have RB equal to -6. Now to solve for deflection at C, we cut this beam in our conjugate beam at this point here, exposing the shear end moment. So let's consider the left side of the beam. We have a uniform load. And a reaction at RA, this is 7.5 going downwards, and a shear moment at C. So let's take our direction, assume it is going downwards. Now to solve for deflection, this is basically the moment of our conjugate beam here at C. So we take summation moment at point C, all equal to 0, considering counterclockwise to be positive. So we have MC plus the 7.5 force times its moment arm distance of 2 meters minus the clockwise moment induced by this triangular load, that is 1/2 times the base of 2 meters times the height of 9 times its moment arm distance of 1/3 of 2 meters, all equal to 0. Solving for MC, this is equal solving, we get MC that is equal to -9, which means that our direction for the moment at C should be clockwise. Therefore, this is a negative moment. Now, what this means for these values to be negative, so from our actual beam, the slope here should be moving downwards, as well as this one. And since we get a moment of negative, therefore the deflection at this point here should be going downwards. So for the answer at the slope at A, this is basically the shear stress, the shear force or the reaction found at this point here, that is equal to negative 7.5 at point A and -6 at point B. And for deflection at C, that's the moment or internal moment at this point here where we cut the beam, which is at point C. It has a value of -9, which means that deflection is going downward. And these are our final answers.